Hey, welcome everyone. So this is 4.9 Antiderivatives. So this is the first section that talks about, that's basically part of the integral calculus. So until now, everything that we've been doing, right, applications and just regular problems, it was called differential calculus. And yeah, in all those sections, right, what we've been doing was I was giving you, or we were getting a function, right? So we had a function, and we were expected to find its derivative. So in integral calculus, it's just inversed, right? So let me write it, integral calculus. Right, so the whole operation will be inverted. In the other words, will be given, I mean, not really, but we could think about it this way. We'll be given a derivative, and this solution will actually be a function. Okay, so let me give you an example. It's kind of easiest way to sometimes, right, to explain what's going on. So example 1. So find a function and we'll call it a capital G. Find a function G whose derivative is 3x squared. Okay, so the problem will, maybe I'll show you how normally the problem would look like. So the problem will look like this. So this was an integral symbol, and then we'll have 3x squared. Then we'll have dx. So that's that dx is in a sense just tells us what variable we're supposed to be kind of solving this for, right? So this will be an integral with respect to x. Okay, so that dx, for now, right, we can think about it this way. For now, that's what that dx means. So that will be the problem, and we'll have to find the solution of this integral. But we could also think about it like this. So let's say I have some function, right? So some kind of, I'm just going to write it like this, and I'll take a derivative of it, and I will get 3x squared. So I know you guys probably already know what's going on, what that is, right? So that function under derivative is x cubed, right? So I hope you knew that. So we could write it like this. So x cubed, right? Now I'm taking derivative of it. Is 3x squared. Right? So normally we were looking for this, but now we'll be looking for that. So if you remember inverse function, that's basically what is happening. There is another thing going on. That another thing is that if I took derivative, let's say, of x cubed plus 2, right? So derivative of that will be the same thing, right? Because derivative of 2 is 0. So that could be x cubed plus any number, right? So it could be plus 28, x cubed minus 64, right? And the answer would always be that 3x squared. Okay, so let's go back to that notation with integral. All right, let's actually go back, right? So let's answer the question. Let's solve the problem. So find a function g whose derivative is 3x squared. Okay, so the way we'll do it is, right, so our function was f of x is 3x squared. So now the function g whose derivative is that 3x squared, right? We know what it is, x cubed. So I'm going to write g of x equals x cubed. And now, right, instead of, right, so right, you saw that that solution actually was x cubed plus any constant, any number. So I'm going to denote that constant as c. Okay, so that's one way of writing the solution and the problem. The other way, right, that we'll be using normally, usually, would be like this, right? So that integral of 3x squared. Now I'm writing that placeholder, that kind of indicator of what variable we're integrating with respect to. So that's x. So that's going to be x cubed plus c. So I hope you understand, right, what I'm trying to to say. Initially, we'll be using this notation. But in general, right, we have that, right, you probably have seen that integral symbol, right? That's basically what is usually used. Different context, right? Let me give you a definition of that. What actually is called the antiderivative. Antiderivative is like, you know, in my country, in Poland, we don't have that type of terminology. We just use integral, and that's it. We don't have antiderivative. But here, I guess we have antiderivative, so here's the definition of it. So a function g is called antiderivative of f on some interval, on an interval I, if g prime of x equals f of x, right, for all x's in I. Okay, so let's make a comment about that c. So if g is an antiderivative, derivative of f, then so is g plus c. Okay, so yeah, let's do more problems, well, more examples. Example 2. So this time it's basically the same thing. It's just worded differently, and it goes like this. So solve a differential equation so differential equations are a topic for calculus 2. Also, there is separate classes where you would be solving differential equations. Anyway, yeah. So here's a differential equation. Differential equation basically is just an equation that has that y prime or dy dx in it. Well, right, with variations, and and here, right, when you have a differential, when you have a regular equation, like say, I would maybe let me come up with something similar, right? So, right, 4 equals 2x plus 3. Right, so if we're solving something like this, the solution would be a number, right? If you're solving this, the solution will be a function. Okay, so that's what differential equation is. As I said before, right, it's a topic for calculus 2. Anyway, so let's solve it. So we're trying to find a function, right, whose derivative. Let me write it like this, right? So we're trying to find some function, equation, expression, whose derivative would be that 2x plus 3. Right, so we're just kind of looking at this 2x and thinking, well, what, right, some kind of expression that would give me whose derivative would be 2x. Well, that will be x squared, right? X squared. If I took a derivative of x squared, I would get 2x. Then the next term is 3, right? So I'm thinking about, right? So that was that first. To get 2x, I take a derivative of x squared, right? To get 3, I take a derivative of 3x. And then, of course, I have that c, right? Because that solution, that function, right, could have any constant right there at the end, right? That constant could be, this could be 0, right, as well. Anyway, we don't know what that is. And kind of that's how it is, and this is our solution, right? So this is that function that would solve that as a solution of that differential equation. Okay, so another example, example 3. So now, let's write it like this. So find antiderivative of this f of x equals cosine x. Right, so we're looking for the g of x. Right, so the g of x. Right, so we're thinking, well, what function, if I take a derivative of that function, would give me cosine x? Well, it's sine, right? It's the sine of x. So we have that sine x plus c. Right, we always have that plus c because right, derivative of any constant is just 0. And we don't know what that constant is. So we need to include it as just that c. Okay, so yeah, I introduced at some point, right, a couple minutes ago, I introduced this symbol. So notation. That symbol was it's called just integral sign, right? So looks like this. Then we have the function, of which we're taking that integral d of x, and then antiderivative, right? The solution is another function plus that constant. Okay, so this is that fancy s, or it's just integral sign. There's no other name for it, right? So this is integral. I mean, it's not s, right? It's just a sign for integral. But yeah, looks like kind of like s. So the function that we're taking integral of is integrand Okay, so this is the variable of integration. Okay, we have that, and yeah, so this, let me rewrite it here because it's just messy up there. So g of x plus c. So this is called antiderivative. And this is called constant of integration. Okay. Yeah, so now basically we just do problems, right? There are some rules of integration, right, that are kind of inverse operations of taking a derivative of something, of differentiation, and I'll show them to you in a moment. But let's just get familiar with that symbol and with just taking integrals. So example, I have 4. Okay, so compute. So this is how a normal integration problem would look like. Compute an integral. So that's how, say, in my country would problem be described, right? As I said, we don't have this idea of antiderivative. We just kind of solve integrals, and here's the integral. So integral of x to the 5th. It's all in parentheses here. Plus sine x plus 3. And then we have that dx. Okay, so yeah, without further ado, we're just gonna go for it, right? So I'm thinking, okay, so x to the 5th, right? So what would I have, right? What expression, what function would give me x to the 5th if I've taken a derivative of it, right? So I need to have, right? Remember how differentiation works, right? So it works, right? So now I'm talking derivative. I'm thinking about derivative, right? So to get x to the 5th, right, I need to have x to the 6th, right? So x to the 6th. Because, right, so the rules of differentiation tell me that I need to subtract 1, right, from that exponent. So if my exponent is supposed to be 5 after I've done that, right, that differentiation, I need to have 6. But also that 6 goes to the front, right? So it's going to be 6 in the front. But since that goes to the 6, I mean that 6 goes to the front, and in my integral, so here, I don't have that 6 in the front, right? So I need to somehow accommodate for that. So to do that, I'm going to erase this, by the way, right? So I'll have that 6 down here. Okay, so now if I take a derivative of that, let me erase that part, this part, and this part. And if I took a derivative of this, that's not what I meant to do. And so I'm taking derivative of that. Derivative, that's a prime. I'm going to get x to 6 minus 1 divided by 6. And there was a 6 in the front also, right? So the 6's cancel out. This is going to be, well, this doesn't cancel out, it's just x to the 5th. X to the 5th over 1, and that's x to the 5th. I hope you understand what I'm talking about. If you don't, in a moment I'll give you a formula for doing those integrals. Anyway, basically I have x to the 6th divided by 6. And now I have plus sine of x, right? So I'm thinking, what do I need to put here when I take a derivative of that? I get sine of x. Well, it's negative cosine of x. And then I have plus 3x plus c. Okay, so yeah, simplify that cosine, so x to the 6th over 6 minus cosine x. Okay, so yeah, you guys see what's happening, right? So now we solve that integral. This is the solution. We can check it, right? If you took the derivative of that, it should give you this. Well, check it and see if that's true. But also, right, another thing is that we see what we have, right? What we actually did, right? So we took, when we look at that first term, I'm talking about this, right? So I took a derivative, I took an integral of x to the 5th dx, right, with respect to x, and I got x to the 6th over 6 plus c. So you see what's happening. So what is happening, right? So this was 5, right, and now it's 6. So what happened, I added 1. Let me erase this part here, okay, so that you can see it better. So I added 1 plus 1. So 5 plus 1 is 6, right? And then I took that exponent, and that exponent ended up in the denominator. So you see, everything is reversed. I'm going to erase that, right? Because it's not what we're what we're really doing here, right? This cannot be this expression cannot be under the integral. Anyway, so it's reverse operation, right? So when we were doing derivatives, this went to the front, but it went to the numerator, and it went there before we subtracted 1. Now everything is reversed. So first I'm adding 1, right? I'm adding 1 to that exponent, and then I'm not putting it to the front, right? I'm putting it kind of in a reversed, so I'm not going to multiply, right? I'm going to divide. Okay, so exactly everything is reversed. Okay, so this is dx. Yeah, so we could, you could, right? I basically just told you what that rule is, right? For integration, for simple polynomial functions. So let's write it. So rules of integration. Okay, and yeah, for now, the rule is going to how should I? Maybe we should write it kind of as differentiation here, so derivatives here on the left, and integration here. Maybe that's a good way to kind of compare them and explain it, right? So derivative of a number of constant dx of c is just 0. Now integral of 0 is that constant. Okay, so let's leave it like this for now. Now we have d dx, so derivative of just some simple k times x, right? So 3 times x and the number times x is just that constant. And now integral of that k, right, is going to be that kx, right? Kx, and of course there is that c, right? Okay. So the general rule, right? So these are just kind of two simple integrals, and then we'll take a look at them in a moment again. For now, let me give you that how is it called? I think it's power rule. So power rule of integration, or for integration. Okay, so it goes like this. So if I have an integral of x to some power with respect to dx, right? So I'm kind of going back to this example here, right? So now, when I was taking derivatives, I was adding, I was subtracting one, or I was moving that n to the front, right? I was just talking about it, but here we're doing the opposite, right? As I said. So first we're adding that 1, right? So it's going to be x, n plus 1. So in differentiation, I was first moving that n to the front. Now I'm not doing that. I'm adding first, right? And then in differentiation, I was subtracting 1, right? That was the kind of the second step here, right? It's the first step. And then that n plus 1 is going to go here. And then we have plus c. Yeah, so yeah, we can check it, right? So because now if I take a derivative of that, of what I have here, I should get this, right? All right, so let's do it. So let's do d dx, right, of this whole expression. So x to n plus 1 divided by n plus 1. And that is... Okay, so how does it work? So it works like this, right? So first step was we take... And now I'm taking derivative. And they're taking derivative because I'm checking if I take a derivative of that, I will get this. Well, will I? And the rules of differentiation say, right, I take the exponent, put it to the front, plus 1. Then I still have that n plus 1 here, n plus 1. I'm supposed to subtract 1, right? And this n plus 1 is still here. Okay, so you see this? This cancels out, these two cancel out, and I end up with x to the nth. Okay, and yeah, that's what we were supposed to get. Yeah, and basically this rule works for a lot of different expressions. One of the expressions that it doesn't work for is let's do this kind of side note that right, so we're taking the integral of 1 over x. Okay, let's see how that works. Dx. Okay, so what we're supposed to do, we're supposed to, let me right, so we're solving, but what we're actually doing is taking integral of x to negative 1, right? We want to have those exponents, those rational functions or rational expressions, right? I'm talking about something over variable, written in this form, in exponential form, right? I want to have that -1. The same go with, like say cubic root, right? Cubic root of x. I want to have an exponent. It's just gonna make things easier. Okay, so what does that rule say? So the rules say, first, right, I'm adding 1. So I go x to -1 plus 1, and I'm taking this exponent, right? And this exponent goes in the denominator. Okay, so that is -1 plus 1. Okay, so if it's x to the 0 power over 0. Right, so we're dividing by 0, so it's undefined. Right, so we can't use that rule for every problem. This integral actually have a solution. It's just we cannot use that particular rule. Okay, so yeah, let's just do more examples, and then I'll give you a bunch of practice problems, and that will be it for the first section on integration. All right, so example 5. I don't know if that's right, but that's what I have here. Example 5. And it goes like this. So let's just write compute integral. And here's the integral. X plus 1 on the top. Radical x here. Dx. Okay, so as I was saying, it's a good idea to change that rational expression to just kind of expression where that variable in the denominator is expressed as an exponent. So let's try to do that and see if it's helpful. So we have x plus 1, right, times x to -1/2, right? So that dx. So dx. So that this part is that part. Okay. We could keep going with this, and I would have. Let me write it maybe here, a little bit lower. So now I'm distributing that this to those two, right? So I'll have x. I'm distributing that x to half, -1/2 power to x first. Right, so I have the same variable, so I can add the exponents. So it's gonna be 1, right? So this is 1 plus this, so it's gonna be x to half, x to 1/2. And then I hope I can go back. Yeah, let me finish that writing this, and then I'll get a little support hand for my hand. Anyway, so it's x to 1/2, right? So this came, right? Let me explain it again. Distributing that. This came from multiplying this by that, right? So it's just a simple distributive property. I'm adding the exponents, right? So 1 plus -1/2 is +1/2, right? So that's where this came from. It's just algebra, right? And then I have plus. And now I'm doing 1, right? So now I'm here. 1 times x to -1/2 is just the same thing. X to -1/2. And we kind of know what to do with an integral like this, right? So we'll be basically calculating two separate integrals, right? Of that plus that. And the reason I left that space here, right, is that we can take this integral and we can take this rational expression and we can separate it, right? It's going to be x over that and 1 over this. Okay, so let me rewrite it. Just to give you this kind of algebraic tool, right, of solving integrals, right? It's kind of splitting the integral into 2. And then I have plus 1 over radical x dx. Okay, so now I have 2 integrals. So we have x over radical x plus integral. So also I need that dx there. And let's keep everything the way it's supposed to be. So I have dx and then plus, I have integral. Now I have 1 over radical x dx. Okay, so that basically equals this, right? So I hope you understand how it happens, right? So when we look at this, right? So now I'm dividing, right? So I'm dividing, make it a little side note, right? So it's going to be x to the first power, right? I'm dividing. So in other words, let me do it a little bit slower. Maybe I'm like, I don't know, giving you too much information or making it too complicated. But it's just algebra, right? So when we have, let's look at this. So x to the half, right? So when we have division and we have the same variable, we subtract the exponents, right? So we do the same thing as I did over there, right? It's just slightly different way. Minus, I'm subtracting, right, those exponents. And yeah, and this is still half, right? And then this is 1 over radical x, square root of x. Square root of x is 1 over 2. It's the same as, right, is negative 1 over 2. Because negative pushes the whole thing down. Okay. So I hope you understand this algebra. Let's go back to calculus. Okay, so there are 2 integrals. Right, so actually I'm here. Now I don't know how to undo it. Anyway, right, so this still here, dx. That's I'm looking at this. This is probably the step that would come after here. Okay. Anyway, so that equals, so integral of this so here, integral of x to the half. Right, so let me do it slowly. Okay, so I have x to 1 over 2. I'm adding 1 plus 1. I'm taking that exponent and putting it in the denominator. Plus 1. And then I have the second integral, this one. Same thing. Adding 1. So plus x to negative half plus 1. Whatever that exponent is, it goes in the denominator. Plus 1. Okay, so yeah, now we just have, fractions. So this is x to 1 plus half is 3 over 2. And here 1 plus half is 3 over 2. The other one, is that plus c also, right? Let me write it in a different color actually, because it kind of gets lost there. So plus c. Yeah, so that's plus c, right? So a lot of students, people, including me, forget that plus c. And, that c is supposed to be there. People forget. And that's kind of how it is. Anyway, so that second integral, right? So half plus 1 is x to 1 over 2. And here on the bottom, I have 1 over 2. Okay, so we simplify it. And we get... maybe let's write it like this. Right? So it's just kind of simple arithmetic. 2/3 x to 3 over 2 plus, right? So divided by half is the same as multiplying by 2. And then we have the plus c. Okay. Yeah, so basically that's how it works. This was kind of difficult example. Right now, right? There, of course, integrals are much more difficult. There's a lot of integrals or a lot of functions whose integral is just impossible to find. But for now, let's deal with a couple of problems for practice that, are relatively easy to find. Anyway, so here we go. So integral of x plus 7. All right, then problem number 2. Integral of 2x minus 3x squared. So I didn't officially kind of tell you that or give you some kind of theorem or definition, right? That we separate, something is missing here, parentheses. That when we're adding or subtracting expressions under that integral, right? So an integral and then two terms are being added, right? So this can be rewritten as integral of x dx plus integral of 7 dx. Right, so I haven't really officially told you that, but that's kind of what the rules of integrations are. When we have multiplication instead of that addition, that doesn't work this way. But for now, right, all problems will have addition or subtraction. So you can separate those, split those integrals, right? There'll be two integrals. Anyway, let me keep writing. So problem 2, problem 3. And it looks like this. So similar to what we just did, so x plus 6. And then the bottom is radical x. Okay, and then dx. Problem 4. Again, integral x squared plus 2x minus 3 divided by x to the 4th dx. And then integral of 5 cosine x plus 4 sine x dx. And one more. So we have problem 6, integral of theta squared plus secant squared theta, and we're integrating with respect to theta. Okay. Yeah, so try these problems and see if you get the same solutions as I did. Show work as usual if there is any other work involved. So the solution for the last one is theta to the 3rd power over 3 plus tangent here, tangent theta plus c. Okay, the previous problem, do I have space? Maybe. Okay, so it's 5 sine x minus 4 cosine x plus c. Okay, so that was problem 5. Problem 4. Solution for problem 4 looks like this. So negative, yeah, let me just write it this way. Save space, negative x, 1 over x minus 1 over x squared plus 1 over x cubed plus c. Okay, problem 3. I have 2/3. Right, so it's kind of almost the same problem as before. And then exponent here is 3 over 2. And then plus 12 radical x plus c. Okay, problem 2. So I hope those first two were easy for you. Solution for problem 2 is x squared minus x cubed plus c. Okay, and the first problem, problem number 1. Solution is x squared over 2 plus 7x plus c. Okay, so that is it. So this was the first topic of integration. And in a sense, this is the most important topic. In a sense that when you get to calculus 2, calculus 3, right? These are things that your instructor will expect you to be able to do, right? So, say I'm teaching calculus 2, so yeah, there are topics in integral calculus that are difficult, right? That you see later. That I would not expect you to remember, but I would and I will expect you to remember how to do simple integrals like that, and of course those derivatives, right? All those chain rule, product rule, etc. Right? But this, if you can do integrals like this when you enter calculus 2, that's just yeah, that's a good start. That's great. Anyway. Yeah, we'll continue the next section later.